Kiddos, on the backboard, we have a homework due.
Tomorrow.
Should have been today. Awkward, but yeah, it's due tomorrow. I don't need to hear extra comments. Not yet. In your homework, there are quite a few problems. Can I show you, just a little bit of what's going on? Ooh, look at all those polynomials. Let's zoom in a little bit. How nice are these polynomials? 4th degree, 5th degree, 3rd degree. Oh my goodness, they're going to be awful. Look at this section. It just says write it as factors and find the zero. This entire section is all about, oh yeah, that's right. Isn't the title of this section Zeros of Polynomials? Okay, so pause. That's the second page of homework. What's going on in the first page of homework? A lot of vocab. And then we have some graphs, right? No. Hold on, pause. For those of you that started homework, you should have been able to do the first, 1 through 18 without even doing crazy work. Peanut gallery. Shush. You know what that means? The little people in the stands. You shouldn't be presenting. I am. So, shh. Be a good audience and listen. At least for right now. Oh dear. So this first section says determine the number of zeros of the polynomial function, right? Wait, you don't even have to find them? You just have to find how many? Oh sweet, that's cool. So he has 1, he has 2, he has 3, he has 6, he has 6.
7.
No, add them together.
He has 7. Wait a minute. Now it's not moving. I don't know
13.
why. No, not 13.
Oh.
He has 7.
Why?
What?
Oh, is it the highest one?
But wait.
6 is the highest.
I need to review something from yesterday. We're reviewing the fundamental theorem of algebra. The very first thing you should have written down in section 2.5. This has, your answer to this would be 6 zeros. Nope, sorry, 7 zeros. Because the number of zeros corresponds to the highest degree, aka the degree of the polynomial, because the degree of the polynomial is the highest one. Okay. He's a 7th degree polynomial. He has 7 zeros. But wait. Why does that ring really, 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 really wrong, hopefully, to most of you? If I pull out x to the 6, isn't it just 1 minus it? And isn't it just 0 and 1?
Oh my goodness.
There aren't 7 zeros. There are 2.
0 has a multiple.
Possible zeros. Imaginary.
Okay, pause. That's the problem. The directions, maybe you guys can't see it. The directions don't say possible. They don't say imaginary. See, it says the number of zeros.
The actual number.
The actual number of zeros. So here's the struggle. This guy has 7 zeros. Oh, awkward start. This guy has 7 zeros, but did you guys see what, or hear what Emily said? Oh, is it you too? Oh, or Claire. I forget who said. What's the multiplicity of that? So here's the dealio. Hold on, pause. You're going to have something that we call repeated zeros. But then you're also going to have what I think Jaden said, which is imaginary zeros. So here's the struggle. Not every single question of homework wants absolutely all the zeros. How many zeros does every single polynomial have? N zeros. N being the degree. They have that many zeros, but some of them are repeated and some of them are imaginary. So hold on. Do you guys see the very next section title? What kind of zeros are we supposed to be finding?
Rational.
Rational zeros. Okay, hold on, pause. We need to do a quick little recap, a quick little review of our numbers. I know that's weird, but it's true. Ready? Numbers. The big, overarching classification of numbers is complex. Well, yeah. Because complex has reals, has imaginaries, and has reals with imaginaries. Complex includes both. So if it says find all the complex zeros, what do they want? All. If it says we want all the real zeros, which ones can we ignore? Any ones with a negative under a square root from the quadratic formula or from solving. We can ignore all of those if it just says real. But the problem is, we just looked at directions in homework and it didn't say real. What did it say?
Complex.
Rational. Well, okay, so we must have another classification of numbers. reals, we have rationals, and we have irrationals. Not the point, right? Rationals and irrationals. Rationals are ones that can be written as a ratio, which could be decimals. 0.33333 is a ratio, is a fractional number. So it could be decimals, but only decimals that can be written as fractions. There can also be nice numbers, like like 5, or -7, or -1. Fractions, negatives, positives, whole numbers, those are rational. Irrational are the nasty 2 plus or minus √3 all over 5. Now that's a thing that can happen with the quadratic formula, yeah? So we have the possibility of irrationals coming out, but if they're asking us just for the rational ones, do you guys notice they're just asking for the nice real ones? Do you see it? So if they say this in homework, it's saying, just give me the nice real ones, please. But what if they take away the rational title? Then give me the nice and nasty real ones, please. What if they take away the real title? Give me all of them, the real and the imaginary, nice and nasty. You kind of see where the directions are going to lead us? Emily.
The rational one, could you make it into a rational number?
Not this. If it was square root of 4, yeah, but if it's square root of 3, this is a decimal that never repeats and doesn't have any sort of fractional equivalent. So guess what else is irrational? Any nasty square, any radical that can't be simplified, no perfect, like any radical that's not a perfect square, perfect cube, or perfect whatever, are going to be irrational numbers, and anything like 3.1415926, no pattern, or E 2.7, oh no, E has a pattern, 2.71828. Maybe E's not irrational. Ooh, that's a good question. I don't know. Anyway, Brianna, do you have a question? Okay. So wait. Let's go back to homework, okay? So, even though we can say, he has 7 zeros, he has 3, he has 2, he has 1, he has, okay, even though we can say that, when we get here, are we necessarily finding all of them? So anytime you see the word rational, I want you to think nice, real. Now, nice, real, what were you guys writing at the beginning of notes today?
The steps. The goal.
Right? The goal. Rewrite a polynomial as the product of linear and or quadratic factors with real coefficients. But do you realize the possible zeros here? I need you guys to add a word. It's a super important word. To identify what we're doing when we do plus or minus, the factors of the constant, the last term, over factors of the leading coefficient, the leading term. We're not finding all the possible zeros. That list is not all the possible zeros. It's all possible rational. This only gets me my nice reals. That's it. This only gets me my nice reals. But guys, think about it. Don't we want to start finding the nice ones? We don't want to start by trying to look for the nasty ones. We want to start by looking at a narrowed down list saying, these are the nice ones that if they work, you should use to break it down. These are the nice ones, the narrowed down list. Of these are the possible nice ones, the nice real ones that you should use. Now, use, how do we use them? If they work. Right? Remember, we test each of them in f of. Either you're plugging in and seeing if it's 0, or you're going to synthetic and looking for a remainder of 0. Remember, you're trying to find the zeros. But if you find one plugging in at 0, or if you do a synthetic and the remainder is 0, how does that help? How do we use the nice ones that work? What do we use them to do? What does synthetic division do? Doesn't it break it down? It doesn't break it down all the way, but it breaks it down 1 degree. We can break down a fourth to be a third and a third to be a second. Why do we always love getting second degree polynomials? What are those? Oh, it's a quadratic. We can use the quadratic formula. We can do some maybe nice x factoring. We can do quadratics. We can't do 4th or 5th degrees until we break them down, and we can't break them down until we know, guys, to do synthetic with. So what did we do yesterday? We had 2 nasty polynomials, didn't we? Bloop, bloop. We had 2 nasty polynomials. One of them, we took it all the way down. We said, okay, all of your factors over all of your factors. These are our, not all the possible zeros, but all the which ones? Rational ones. All the nice real ones. These are all the nice real ones. Please, some nice ones work. And we found one, oh, no, awkward. Remember, I did some bad math. 2. We found 2 nice ones. And from those 2 nice ones, we were able to break them down twice. And if we broke down his degree by 2 levels, didn't we get to a quadratic? And once we got to a quadratic, weren't we able to bloop, 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 find all the zeros? But guys, look at the directions. Even though we were able to find not only the real ones, but also the imaginary ones, what were they really only asking for? Which is why we only circled the nice real ones, and we ignored the imaginary ones. Now, what was I doing over here when I set up this little fraction? Yesterday, at the very end of yesterday. Why did I write down 1 1/2, 3 3/2? Where did that come from? The formula, yeah. And where did the 1 and 3 come from? What am I looking at? Yeah, good, the constant. Where did the 1 and 2 come from? I was looking at the leading coefficient. Do you see what we were writing today? We have the constant over the leading coefficient, and then I try to pair them up. So 1 over 1, yep, I did plus or minus him. 1 over 2, yep, I did plus or minus him. 3 over 1, yep, I did plus or minus him. And then 3 over 2. Now the nice thing is, whoa, why did I go straight to using 1, besides the fact that he's the easiest number? Oh, that's right. What did we do over here? How did I know he was a 0 if we hadn't done synthetic yet? I plugged it in, and I realized, hey, plugging in 1 gets me a 0. Sweet. Let's do synthetic. And as soon as I did synthetic, I got a quadratic. And why do I not need to do any more testing, any more plugging in? I can just go. What do I have now? A quadratic. So let's go for it, guys. Can you finish this guy off? Because it says to factor the following polynomial as much as is possible. So how do we factor if we have a 2 in front? What do we got? Is it okay if I do my star?
No, you can't just
I can't do the star.
Need groups.
Okay, you do what you like. So I have 2x minus 1 and x plus 3. Whoa, no it's not. It's 2x plus 6. Nope. Remember what you gotta do? My directions were to factor, and I factored. And I just happened to have nice factors. These are all nice factors with real coefficients, which makes life a little bit nicer. I heard a question. Who did I lose? Oh, remember in my star trick, we just take the 2 and we write them on top of what we had, and then you reduce. So that's a 1 and a 3, 1x and 3, 2x and negative 1. But you can do grouping too. But why am I stopping? Well, guys, what does my direction say? Factor. So do you see how you have to pay super close attention to the directions? Okay, let's go back to homework then, just for a second, because we have a lot to do today, but I don't want you guys to get to a section in homework and do it all wrong. That'd be so sad if you go and then grade it later and it's a mess. So, for this first section, weren't you just figuring out how many zeros? Right? Oh, stink, I want to get rid of, oh, no. I promise I'm not this slow, just if you notice my mouse lags and, ugh, that's a mess. Okay, let me zoom out a little bit. This one says how many zeros? Oh, 1 and 2 and 3 and don't do too much work. It just wants to know how many. What does this next section say? Look at the graphs to find the, oh. Do you guys know what the rational zero test is?
No.
Rational zeros, nice zeros, test. This little thing that I'm having you do, that's the rational zero test. This little thing right here in your notes, that's the rational, oh look, it's in our notes, rational zero test. List them all out, that's it. List them all out, and in this listing will be the nice ones. In that listing will be the nice ones if a polynomial has nice ones. So rational zero test, it's just this fraction due. So rational zero test, you're going to take plus or minus 2 over plus or minus, 1 and 2 over 1. And then you're going to look at the graph and say, hey, does it have all the nice ones? Because the nice ones will show up nicely on the graph. Imaginary ones don't show up on a graph, and irrational ones will show up at really awkward places in the graph. So they're just saying, like, hey, do the plus or minus factors of the leading coefficient in the denominator, constant in the numerator, and make sure these zeros line up and they are in that list. Okay, that's just looking at graphs. How about this next section? What's this say? Find the zeros. Which zeros? Yeah, so technically what you could do, if you wanted to, but you don't have to, you could do what we did yesterday, how we were like, hey, let's list them all out and find the nice ones. You could plug in every single one of the possible and just find the only ones that are 0. Or you could use synthetic if plugging in gets nasty. Now, period 3, regular pre-cal is like, it's not going to be hard. I'm just going to do it in my calculator. Why would I have to say on a test a calculator would not be allowed on these types of problems? Well, yeah, so much easier, but also, why not just go to your graph and find your zeros and forget the whole thing? You can't have your calculator on half of the test, so we have to know how to do math without a calculator. Bummer! So, here's the struggle. Some of you who were like, I'm just plugging it in my calculator. You're right in that you're going to find the zeros in the right spots, but you're not really practicing for what's really coming your way because you're pretending like you can plug in when maybe with 6 and -6 and 3 and -3, plugging in would be an awful idea, and you should do synthetic instead. Oh, struggle. Can I get you guys as a group just talking about... He's just like, you're good. Thank you, though. Izzy was ready to go and get out of class. Look at that. Can I show you guys the section of homework this comes from? Is that okay? Because we were talking about reading directions, figuring out what to do. This problem comes from the second page, right over here at the top. What does this say? Use the given 0 to find all the zeros. Wait, like the nice ones? The real ones? Or all of them? Stink. We're looking for the nice and the nasty reals and the imaginaries. Aw, poo. Okay, but what's it say to do? Use the... Okay, so who's the given 0? Huh. Well, once we find ones that go in, don't we normally do synthetic division, guys? But can I do synthetic division with 1 plus 3i? I need a polynomial. Or I need an x minus. How do I do an x minus with that guy? That's kind of nasty. I wonder where he came from. We're going to come back to this guy. If you guys don't mind, if I were you, I would leave something like, I don't know, 4 or 5 lines. Can you go find an easier guy and then come back to him? This one's a little bit easier. It's another find a polynomial. Some of homework, actually a lot of homework gives you hints. Because it's really hard just to say, here's a huge polynomial, go. Like, if there are tons of those, it'd be awful. So they give you hints. And so here's an easier hint. Skip 4 or 5 lines. We'll come back. Here's an easier hint. What do you guys see that they've given us? Who are some guys that we know already work?
Zeros.
The zeros. Okay, so we want to make the polynomial. Well, if these are the zeros, then guys, what factors did they come from? Okay, so we have x plus 1, x plus 1. There's 2 of them, right? That's nice. They wrote it twice. They could have said multiplicity of 2. Well, I mean, I guess I can write them, right? The same way I write x plus 1 and x plus 1, I can write x minus 3i. But why do I have an extra set of parentheses if they don't tell me anything else? There has to be 4 because it says there's a degree of, and that's x to the 1, x to the 1, x to the 1. I need 1 more. Does anybody know what that 1 more is just based on these 3 zeros?
0.
Why does it have to be x plus? Yeah, think quadratic formula. Don't the i's come from the square root of the negatives? And in the quadratic formula, don't we always have a plus or a minus? So we have a negative, we have an x squared, a plus or minus square root. Oh, so if they tell us 1, guess what we know? It's an understood other one, which is a little bit nasty. They were kind of mean. They only gave you 1, but there has to be both. Now check it. What do you think? Are we allowed to box it and be done according to their directions? Because what do we have right now in one of these factors?
Imaginaries.
Yeah, we have imaginary, so that's no good. But don't we have all the factors, guys? All 4? So how do we make this look more real? Yeah, where did this come from? Aren't these a difference of squares, and can't we make it x squared minus 9i squared? Aha! My imaginary is about to be gone. Why? What's I squared? Do you remember that these imaginary dudes come from a sum of perfect squares? Not always. You can always have quadratic formulas also that couldn't be factored any other way, and the negative b plus 9 squared root b squared minus 4ac. Imaginaries come from there too. But these little baby imaginaries, it just came from a sum of squares. Now, technically, well, hold on. We also have the x plus 1 squared, right? How do we do this guy? He's not a difference of squares, so a squared plus 2. Yeah, a squared plus 2ab plus b squared, or foiling x squared plus 1x plus 1x plus 1.
Or 4.
Is that a polynomial? Yeah.
Or 4.
Yeah, they actually want us to get the whole thing. Are you serious? Yeah. They are. But if we were to do the full polynomial with all of the foiling and distributing and all that jazz, because he has to go to both, and then he has to go to both, and then he has to go to both, we would end up with, at the end of the day, an x to the 4th, we would have plus 11x cubed. Because we have this 2x squared and that 9x squared, and, or x cubed, so 2x cubed and 9. Oh, no, that one. That's a 9x squared.
Yeah, 9x squared.
We just had 2x cubed. And then we have a 1x squared and a 9x squared, so 10x squared. And then we have 18x. I think I did it fast. Don't judge me for making a mistake. But we find our polynomial. So sometimes it's nice because they give us the clues and we just have to work our way back to the original problem. But in other problems, guys, we're going to have a big old nasty polynomial and we're going to have to go looking for plus or minus 1, plus or minus 3, plus or minus 9 over 1. But maybe, do you think we could find one pretty quick? And do a synthetic and break them down and then find, oh, this one would be nasty. It was like Izzy's yesterday. This one, the negative 1, does work twice. But then eventually we'll get to a quadratic that we can then go ahead and find our imaginary zeros with. But anyway, if they give us hints, guys, they've given us part of what's there. Now this one actually kind of gave us everybody and we had to find the polynomial. But can we go back to that one that we just had a second ago? Ugh. Ugh. So, it's a little different. They haven't given us all the factors, they've only given us one. But according to what you guys said a second ago, wait a minute, if we know one imaginary, what else do we know?
There's another one.
There's another one. What would the other imaginary be?
1 minus 3.
Okay, does that make sense? Quadratic formula, plus or minus. Okay. How do we factor? They've given us a hint, because do you see why they've given us a hint? Do you realize it'd be 1 and 2 and 3 and 4 and 5 and 6 and 10? Right? And 6 goes with 10 and 5 goes with 12 and 4 goes with 15 and 3 goes with 20 and 2 goes with 30 and 1 goes with. Do you want to try all those?
Not
How about
really.
you?
Well, you can just do plus or minus all
So,
of them.
don't we know this has 1 and 2 and 4? Don't know those two. But I do know this is x minus, okay, you're about to get really sad. And x
Oh no.
minus,
This is that y. Oh my goodness.
if you want to start testing all of those, it's okay. There's only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 24 different options. Oh no, we're still going here?
Unless you do this synthetic. Can you split it?
But we can't do synthetic unless we have someone to put in the box, right? So you have to try all 24 of those. Sophia, why'd you say foil? Okay, maybe we should take this and give ourselves some room. We're foiling because, guys, a second ago, if we hadn't known the negative ones, which we could have found these, oh my goodness, it's always this class.
It's fine.
Never mind. It's walking. It'll come. If we, guys, check it. If we could have taken these complex numbers, multiplied, figured out where it came from, where they came from, couldn't we have done long division with a polynomial and seen who was left? If we can take the complex ones and figure out where they come from, we can do a division and ask ourselves who's left. So, going back to that nasty one. We're foiling because we want to say, where did you guys come from? Well, you're going to be mad, but oh well. It is what it is. We're going to have an x squared. Hey, it's the easiest one. Outer. We're going to have negative x times 1 minus 3i. Inner. We're going to have negative x times 1 plus 3i. And then last, we're going to have positive 1 minus 3i times 1 plus 3. We're technically foiling. There's just some nasty stuff that we're foiling. But you at least see I'm foiling. X times x is x squared. X times a negative this dude is negative x times that dude. X times a negative that dude is negative x times that dude. And then that dude times that dude is whatever. There you go. Are we okay?
No, I one day.
But Alec, do you at least see the foiling that's going on?
I really don't.
Foiling means first times first.
Oh yeah, but like.
So x times x. And then outer means outer times outer, which is nasty, which is why I just wrote them next to each other.
Okay.
And then inner, which is nasty, I just wrote them next to each other. And last is nasty, I wrote them next to each other.
Okay.
And now I just have lots of distribution. So I have x squared minus x plus 3ix, or 3xi, I suppose. Imaginary teacher goes. And then I have minus x minus 3xi. Oh, hey, they cancel. And then I have a difference of squares where I get plus 1 minus 9i squared. Oh, so that's x squared minus 2x, and then isn't I squared just a negative 1 plus 10? No, that's way nicer than I thought it was gonna. Oh, this came from a quadratic formula of a quadratic that couldn't be factored a nice, pretty,
Where did
neat
2 come
way.
from?
Oh, maybe we should have seen that coming.
Where did 2 come from?
It's, oh, negative 1 minus 1. Negative 1 plus negative 1 is negative 2. And then that was 1 plus 9.
Okay.
So check it. We just figured out by foiling that whole mess, which I agree, it was totally a mess. We just figured out where those nasty imaginary zeros came from. And weren't we just trying to ask ourselves who the other dudes are? Oh. Well then, I should do synthetic. No, don't you dare. Don't do synthetic. That's a long division. I should do a long division. Or I should say, okay, I have to take that nasty x to the 4th minus 3x cubed plus 6x squared plus 2x minus 60. I need to take away that x squared minus 2x plus 10. But if I take them away, it's like synthetic, and then I'm going to break them down and say, who is left after that nasty guy's gone? Can't do synthetic, because it's not a linear. But I can divide and say, I need to get rid of you to figure out who on earth who else is a part of that polynomial. And then I start doing synthetic division, long division. I have to do my very careful division. I have to be very careful with my subtraction, but not killing anything. Negative 3 plus 2 is negative 1. 6 minus 10 is negative 4. And I have negative x, I believe. So I'll get my negative x. Careful subtraction with my division. Make sure you see that cancel. Negative 4 minus 2, negative 6. 2 minus a negative 10 is plus 10. Oh, it's so nice if this goes in evenly. It's supposed to go in evenly because I have it as a factor. Negative 6, please work. Negative 6x squared, so far so good. Plus 12x, so far so good. Minus 60. Boom. Who's left? This guy tells me I know how to fill in. Unless I know how to fill them in. Well, guys, we figured out that this awkward dude, because of the quadratic formula, gives me the zeros of x equals 1 plus or minus 3i. But now we also can take in and say, oh, that's just an x minus 3 and an x plus 2. X equals negative 2 and 3. And those nasty imaginary they gave me at the beginning. Those one. Those one. What made him nasty? It was a quadratic formula backwards. Ugh. Okay. It was a quadratic formula backwards. But, once again, that is not the majority of homework. That is not the entirety of homework. That is one very, very, very unique and small section where some of them are pretty, like the first one we did, and only a few of them are nasty, and I'm pretty sure I only gave you one.
You're running it math having circumference.
Because either we made a mistake here in our division, or here, or the problem was wrong. So you did then it was never possible. Okay, so hold on. Wait a minute. If that's not all of homework, then maybe we shouldn't stop at that page. Maybe we should, make a quick note, because you guys did a great job of knowing that complex zeros always come in pairs. It took you a second to figure it out, but you did figure it out. So if they give us a positive one, we can say the negative one is true. If they give us a plus, we can say the minus is true. So we can say really quickly they come in pairs. A quick little note, just a quick little, oh, this is what the example showed us. A quick little note, a quick little, oh, this is what the example showed us. He's kind of just problem solving. What else could show up in the homework? I think I can. Let me freeze the screen real fast so you guys can get the little note down. Just a little baby note. They always come in pairs. If they give you one, you know the other's true. Okay, the end of notes, guys, are basically just two little like, hey, you see this can get gross. And you see there's not like a nice short little modified x method that will always get us to the answers for factors of polynomials. It's not as nice and sweet as that. So these last two pages, are things that, to be honest, I'm actually going to have you guys put your pencil down after you write this and not write with me. Because I don't necessarily need you to memorize these next 2 pages. I just want to show you how there are tricks to narrowing down a list of zeros. There are tricks to narrowing down a list of zeros. Just a second ago, you guys saw a polynomial that had a last coefficient of a 60. And 60, oh man, there were so many possible zeros. It's disgusting. You just saw a polynomial a second ago that had a last or a constant term of 60. And that 60 had all these. Now, what if this was 12? Because then you would have had the 24 top ones, and you would have had 1 and 2 and 3 and 4 and 6 and 12 as denominators. Oh my goodness. So, there are, at the very end of notes, put your pencil down, don't even stress about it. There are 2 little tests, 2 little shortcuts. Kind of not. 2 rules that could help you take a really huge list of possible zeros and say, oh, forget it. I'm not even going to look any further on that side. I'm not going to look any further on that side, to narrow down where you're looking so you don't get as overwhelmed with exactly what's going on. Let me go this way. Okay. So these are the few more tools that some people along the way have used before technology was able to. Well, someone programmed the technology and their strategies built on all of this math to find those zeros like your calculator does. But besides that, before technology, this could have helped to see if there are zeros and if there are, where they are. Descartes' rule of signs and then upper and lower bound rules. So Descartes' rule of signs, long story short. If you have a polynomial in descending order, the number of positive real zeros, this is what it says, the number of positive real zeros, real, not imaginary, is either equal to the number of variations in sign or less than that by an even integer, which sounds really weird, except, guys, from the third to the second to the first, there isn't a first to the last. Do the signs ever change? Never. So how many sign changes are there? None. So Descartes' rule of signs would say if there are no sign changes, or even if there's 1 or 2 or 3, what can we say? Okay, positive real zeros is either equal to the number of sign changes or less than that. Well, guys, is there anything less than 0? No. So therefore, if you were to go ahead and start looking at, okay, my possible zeros, plus or minus 1 over 1 and 2, Descartes' rule of signs says there's no sign changes, forget the positives. None of the positives will work. And logically, maybe that makes sense. A positive plus a positive plus a positive will never equal 0. But it also says if there were sign changes, okay, we know there's either 2 or 0 or 4 or 2 or 0 or 6, or depending on how big and how many sign changes. The second one says, okay, forget that. No sign changes, no positives. And then the number of negative real zeros is either equal to the number of variations in sign of f of negative x or less than that. So the negative says, check out what happens if we plug in a negative, kind of like symmetry. Oh, wait a minute, how many sign changes are there of this guy when I plugged in a negative and simplified? Just 1. So there are no positives, and there's only 1, or less than that by an even, 1, negative 1, no, it's just 1 or 1, I guess. This one says there is 1 to be looking for. Now, it doesn't equal 1, but there is 1. Wait, if there's only 1 negative to be looking for, then question, what are all the rest of the 3 zeros? They must be imaginary. So, like, we can whittle down what's going to happen with some of these tests. The upper and lower bound rule basically says if you find a 0, and if you do synthetic with that 0 of a polynomial like this guy right here, and if there is no sign changes when you do the 0, he is what we call an upper bound, so don't go looking any higher. And there's something similar with lower bound. At the end of homework might ask you to use the rules, just peek at it, don't memorize them. Don't even stress about writing it down, but it's like, if this is a strategy to narrow down, can I kind of understand what it says? That's it. Bye, guys. Don't stress. Please don't memorize. Only write it down if you're curious. We don't see enough hard ones to make memorizing this necessary. Later, Gators.